Hello everyone and welcome back to the day 2 of our deep learning workshop. I hope you all enjoyed yesterday's session. Yesterday we discussed about artificial intelligence, machine learning, deep learning, neural networks. We also talked about features and labels, how it makes a data set. We also talked about splitting our data into training and testing phases and making predictions out of it. We even built our first machine learning model that predicted students' marks based on their study hours. Today we are going one level deeper. We are going to understand the mathematics that powers the deep learning. Now you don't need to worry. The word mathematics scares many students, but I promise today's session will not feel like a mathematics lecture. Instead, we are going to understand how the machine actually thinks using the numbers. Before we begin, for those joining us for the first time, let me quickly introduce myself. My name is Sahil Sawant. I have completed my B.Tech in Electronics and Telecommunication Engineering from VIT Pune, and currently I am pursuing my Masters in Computer Engineering from VJTI Mumbai. My primary areas of interest have always been artificial intelligence, signal processing, machine learning, deep learning, and data science. Also, remember that this course will be available on Ingeverse. You simply need to create an account, sign in with the sessions, complete the final quiz, and earn your certificates. Ingeverse was built to support engineering students throughout their journey. Whether you are preparing for placements, GATE examination, or semester studies, or any technical interviews, you will find your valuable content there. Currently, we are self-hosting more than 8 technical courses along with premium notes, learning resources. Take a look at this particular diagram. At the first glance, it looks a little bit complicated. There are inputs, weights, activation functions, there are outputs, there are implied learning rates, optimization paths, and there are errors as well. But by the end of today's session, every component on this slide will make a complete sense. Notice that we start with the inputs. These inputs enter a neuron, and neuron combines them using their weights. Then an activation function is the one which decides whether the signal should continue forward or not. And the output is then attained, which is compared with the target. With this, the error is then calculated, and finally the model adjusts itself to improve itself. The entire process is what we call for a machine. Humans learn from their experiences, and similarly, the machines are learning from the mathematics they provide. And that mathematics is exactly what we are going to study today. Now, the question is, why exactly mathematics? One of the most common questions that students ask. The answer is pretty simple. Machines cannot see. Machines cannot hear as well. Machines cannot understand what we say or understand the language. At least not directly. When we took a look at a face, we instantly recognize it. When we hear a song, we identify the singer as well. When we read a sentence, we understand its meaning. Machines cannot do this naturally. Everything must be first trained into numbers. This slide beautifully shows the transformation. On the left side, we have the real world, we have the images, audio, handwriting, text and all. And on the right side, we have the matrices and numerical representations. AI is essentially a translator. It converts the reality into mathematics. And once everything becomes numbers, machines can process it. This is why mathematics is the language of artificial intelligence. Now look at this slide, which summarizes our today's journey. There are 5 major components, starting with the vectors. Then we move on to array of vectors, which is matrices. We will be also looking at the activation functions and the loss functions. And finally, the gradient descent. If you understand these 5 concepts, you understand the foundation of deep learning already. Think of this as a life cycle of learning. The data enters, the network is going to process it. The network then makes a valid decision. It measures the error in the decision as well, and based on the error, it improves itself. The process is repeating. The cycle happens millions of times during training, and eventually the model becomes intelligent. Now let's examine each stage one by one. Moving on to the first form, which is the vector. Now vector is a one-dimensional data. It is the simplest mathematical structure that is in AI, which is vector. Simply, vector is a list of numbers. For example, 2, 4, 6, 9, 10. Looks simple, right? But these numbers can represent meaningful information. Suppose we are predicting house prices. The vector could represent number of bedrooms, the areas, area of property, or suppose we are predicting the student's performance. The vector could represent here the student hours, study hours, attendance, assignment scores, and each value represents a particular feature. Remember yesterday's discussion about features and labels? Similarly, vectors are how the features are stored mathematically. Machines do not see the study hours. Machines only see the numbers. Vectors are therefore the first step in translating reality into mathematics. Now, when the data becomes more complex, vectors are not enough. For that, we need matrices, the two-dimensional data form. A matrix is simply a table of numbers, rows and columns. Images are stored in the form of matrices. Every pixel inside an image is a numerical data. For example, a grayscale image can be represented entirely only using numbers. The same concept is used inside the neural networks as well. Remember the connection between the neurons. Each neuron has a weight. A connection has a weight. Those weights are stored in the form of matrices. In fact, most of deep learning is simply matrix operation only, happening at incredible speeds inside the GPUs. So whenever you see an image, a neural network becomes a matrix. Whenever you see a photograph, a neural network sees these numbers arranged in rows and columns. That's the power of matrix representation. Now, let's imagine a neuron receives some numbers. Should it always pass them forward? No, not necessarily. That's where the activation functions come in. Think of them as decision gates. They determine whether the signal is important enough to continue or stop. Without the activation functions, neural networks would simply perform linear calculations. They would not be capable of learning complex patterns. Activation function introduces some kind of non-linearity. And that's what allows neural networks to store or solve difficult problems such as image recognition, speech recognition, or language understanding. In simpler terms, activation function helps the neurons to decide when to activate. They are the brain of neuron. Now, here we represent two of the most important activation functions. The first one, sigmoid, in which the output lies between zeros and ones. This makes it useful when the probabilities are needed. For example, will a customer buy a product? It is either yes or it is either a no. Will a patient have a disease? Yes or no. Sigmoid converts the values into probabilities. Now look at this ReLU function. ReLU stands for rectified linear unit. ReLU blocks the negative values and stores the positive values to pass. That's it. Simple, yet incredibly powerful. Today, ReLU is most widely used activation function in the deep learning. Almost every modern neural network uses ReLU in some form. Whenever we are building the neural networks in future scenarios, you will see ReLU again and again. Now, let us move on to assume the network makes a prediction. Now, how does it knows whether it was correct or not? The answer is via a loss function. The loss function measures the difference between the reality and a prediction. Suppose the actual value was 100, but the model predicted 80, and the error is 100 minus 80, which is 20. The loss function quantifies this mistake mathematically. This is one of the most important ideas in machine learning. A machine learns by doing mistakes, just like humans. The difference is that the machines can calculate exactly how wrong they are. And that information becomes the foundation of learning. No loss means no learning. Now we move on to the next scenario. We know the error. But what should we do with it? That's where gradient descent comes in. Imagine standing on the top of a mountain. Your goal is to reach the lowest point in the valley. How do you do it? You keep taking steps downhill. That's exactly what gradient descent does. The mountain represents the loss, and the algorithm continuously adjusts weights and biases to move forward, making the error smaller. Every adjustment improves the performance slightly. Thousands of small improvements eventually produce higher accurate results. Gradient descent is essentially the learning engine of deep learning. Without it, neural networks could never improve. Now, let's connect everything together. The data enters vectors or matrices. The data is then processed through neural networks using the weights. Then an activation function is used to make decisions. The decisions are then compared to present as our errors. The errors are measured using loss functions. The gradient descent reduces those errors. The updated weights are then stored as the new ones. And this cycle continues again and again and again. Eventually, the network becomes capable of making intelligent predictions. The diagram here represents the complete learning loop. And if you understand this loop, you have already understood the mathematics foundation of deep learning. Every advanced AI systems from ChatGPT to self-driving cars follows the same fundamental principles. Takes the scale may be larger or smaller. The models may be more complex or less complex, but the learning cycle still remains the same. Now, today we have answered a most important question. How do machines learn? We learned that the reality becomes numbers. The numbers are represented either as vectors or as matrices. The gradient descent improves the performance, which is taken by the activation function as decisions, and loss function measures the mistakes. And this repeated learning rate creates the intelligence. The mathematical cycle is the engine behind artificial intelligence. In the next session, we will move from mathematics to implementing and beginning building more advanced neural networks. Until then, thank you for joining today's session. If you enjoyed today's lecture, don't forget to like the video and share it with your friends and subscribe to my channel. Leave your doubts and questions in the comment section. I regularly review student feedbacks and try to understand or answer as many questions as possible. Also explore endeavors for the course recordings, certificates, quizzes, premium notes, and additional learning resources. And if you are interested in learning more, check out some of our major contents available on Sahil at Work YouTube channel, including algorithms and problem solving playlist, data science with Python, microprocessors and microcontrollers, and other playlists or courses. Thank you everyone for watching this session. I will see you in the next one. Until then, happy learning, keep building and keep learning. Adios.